Hello. So for our group's fifth and final video, I'll discuss our implementation of topologically sorting a graph using the CAN algorithm. So we'll begin in our main file, in which we create a directed graph, add some edges to it, display the graph, and then we create a new topological sort object. We perform a BFS topological sort using breadth first search and print the result. Then we run a DFS topological sort using depth first search and print the result. And so the next thing we have to look at is the graph interface. So the graph is a very simple interface containing some of the basic methods we expect in a graph, which includes get number of vertices, which simply returns the number of vertices in the graph. We have get adjacency list, which returns the adjacency list of the graph, which is just a way of representing the graph as a map from vertices to the list of vertices. We have add edge, which is what it sounds like. This is just a way of adding an edge from vertex X to vertex Y in the graph. And we have display graph, which again, as it sounds like, will simply display the graph when that's implemented in a concrete class. So then to look at a concrete class, we have directed graph, which is a concrete implementation of the graph interface we just looked at. And so this class really represents the graph data structure. So in terms of variables, it has number of vertices, which represents the number of vertices in the graph. It has adjacency list, which is an array of linked lists, where each index in the array represents a vertex in the graph, and each linked list at that index represents the vertices that the index is connected to, i.e. its edges. We have a method get number of vertices, which, as it sounds like, which returns the number of vertices in the graph. We have get adjacency list, which returns the adjacency list of the graph. And then we have this inner class directed graph. So it initializes number of vertices and adjacency list based on the number of vertices passed as an argument to the directed graph. And it's going to build each list. We have add edge, which is going to add an edge from vertex X received to vertex Y also received in the graph. And it's going to do this by adding Y to the linked list at index X in the adjacency list, which we initialized earlier. So we have this adjacency list here. This method add edge is going to take X and Y and then add X at Y. Then finally we have our display graph, which is just, it's going to, for each vertex, it's going to print the vertex number and the vertices that's connected to. So this class overall is used to create a directed graph, add edges between the vertices, and display the graph. And the final big class that we want to look at is the topological sort, which itself contains our two BFS and DFS sorting methods. So the first big thing to look at here is the BFS topological sort, which will accept a directed graph as an argument, and it'll perform a topological sort using DFS. So the first step being, it will find the in-degree of all its vertices. It'll add all vertices with in-degree 0, so no connections to it, to a queue. Add any vertex with in-degree 0 to a sorted list. Decrease the in-degree of all neighboring vertices by 1, and if any vertex has in-degree 0, add it to a queue. We then repeat the prior steps until the queue is empty. So pretty much what we have here are the steps I described above. We find the in-degree of all vertices, any vertex with in-degree of 0 down here. We add it to a queue. Added to our sorted list, Decrease the in-degree of all neighboring vertices by 1 if any inner vertex has in-degree 0 added to a queue, and repeat our steps until the queue is empty. And down here finally we've found all sorted vertices, so we return our sorted list. Next down here we have this DFS topological sort util, which is just a utility method for our DFS sort. All that'll do is start from a vertex and check if there is a cycle in the graph, because of course if there's a cycle then we can't continue with the DFS method. So as I said there, our previous BFS method use topological sort using BFS. This one uses DFS. So here on our actual DFS topological sort, we'll create a result stack to store the result. We'll create a visited array to keep track of all the vertices or nodes that we visited. We'll perform a depth first search on all vertices starting from each vertex which hasn't yet been visited. And if we find a cycle, we'll return an empty list, because when a cycle is found, that means the graph is acyclic. So when the graph is acyclic, we can't perform topological sort. And if no cycle is found, then we add the vertex to the result stack. So that's our entire implementation here. I'll show you what happens when we run main. Let's play. And we get vertex 0 connected to 1 and 4, vertex 1 connected to 2, 3, 4, and so on. So the result of our topological sort using BFS is that the graph is not acyclic, and same again, topological sort using DFS, the graph is not acyclic. Thank you for watching. We have far more depth in our report, and hopefully that goes into enough detail for you. Thank you.